335. In this particular one, we're going to be focusing on project 1. We're going to look at how we can model a partial differential equation using a linear system. Let's get ready and dive in. So the linear system that we're going to utilize will arrive from measuring heat flow along a circular rod. We're going to measure how the heat moves throughout the rod, and we're going to measure it using a function over time. So we're going to measure both its position along the rod, and then also how does the temperature at each of these positions change over time. So that's the main intuition that we're trying to model with this particular approach. If you're not familiar with the partial differential equation, you'll see one in a minute. And the main idea here is to not feel like it's anything extraordinary or exotic. It's really just a function of a single variable, but we have more than one independent variable in this particular case. Okay. So the tools and many of the ideas that we follow through in Math 210 and Math 220 extend to higher dimensions with a similar counterpart. Okay. So today we're going to look at a PDE example. This example is just to kind of get us used to and test the following things: the linearization process, the validity of the approach. We're going to get a numerical result and compare it to the derivative, and then the application to the physical system. So the physical system on the right, we're going to approach with the physical ideas represented mathematically, and then we're going to derive the linear system for that physical system modeled by the PDE. All right, diving in. So our particular differential equation that we're going to look at first is the one shown here. It's a variable in x and t. In general, x and t don't necessarily have to be physical representations, but for us, we will take that x is the position along the rod and t is the temperature when we get to that example. Okay, so we're going to compute the partial derivatives with respect to x and t. We'll start off with t first. The partial derivative with respect to t is, imagine holding u of x and t, where x is treated just like a constant, and we're going to take the regular derivative with respect to t, except for it's not a regular derivative because we have two independent variables in this situation. So the partial derivative notationally speaking, looks like this. You have the partial of t, and it's also written as partial u partial t, is equal to the derivative of u with respect to t, and it's a partial. The little almost 2 looking thing here designates the partial, and here's the function. So this term is 0, this term is 1 when you take the derivative, and then here, using the power rule, the 2 times 2 gives us the 4 that you see here, and the xt left over. Okay, so the derivative with respect to x, do you want to try it? All right, I'm assuming that you've had a moment to give it a glance and maybe take a guess. U of x, the partial u of partial x, we're going to take that derivative, and so this term is going to be 0 because it does not depend on x at all. And this term is linear in x, so that's the resulting 2t you see here. And here we're just using the power rule. We're bringing down the 4 and subtracting 1 from the exponent. That gives us then the 4x cubed here. Okay. Now to calculate the second derivative the second partial derivative with respect to x, we're just going to utilize the result that we have from here and take the derivative one more time. Okay. In doing so, you get u of xx is equal to partial squared u dx squared is equal to, and taking the derivative again of, we already know what u of x was, which is this terms here, and so we get the 2t squared term is constant with respect to x, so it's actually 0, so we don't even need to worry about that. And bringing down 3, we get 3 times 4, which is 12x squared. All right, let's look at the numerical results. In this situation, we're going to choose x and t to be 3, and if we plug in these values, the u will plug in here, and the partials that we're going to get will get here. So for 3 and 2, we're going to plug in a 3 here and a 2 here. So you get that product, which is 12 times 2, which is 24, plus 1 more gives us the 25 here. And u of x for 3 and 2, if we plug in 3 for x and 2 for t, and cube it and square respectively, and then multiply by the constants, you get a total of 116 out, and uxx with respect to 3 and 2, if we plug in those values, there is no 2, so, or no t, so there's no 2 term plugging in. You just get 2 or 3 squared, which is 9 times 12, which gives us the 108. Okay, so those are exact values. We're going to come back to compare these for our linearization schemes and see how well we're doing numerically with respect to these examples. Again, this isn't going to be a proof or anything like that. The comparison is really just to show you that the validity makes sense. Okay, so to linearize a partial differential equation, we're going to start by utilizing the single variable version of the Taylor's series. Taylor's series, if you don't recall from Math 220, I would imagine, is the expansion of a function as a series, as an infinite series, really, of polynomials that approximate and in the limit equal whatever function it is that you're looking at. A couple of notational things. The derivatives will take to the order in which we're going to, and these difference terms here will correspond to the delta step, either in time or in position, respectively. Okay. For the first derivative, we're going to chop it off at the first derivative, and so all of these terms greater than the first derivative we would call higher order terms, so we're going to ignore those. This is the first approximation, and we're going to solve for u prime. Notice here that u prime is a single, it's a prime notation, meaning a single variable. We'll have a very similar analog for the multivariable case. Okay, and so you see here is the u of t with respect to the first derivative with respect to time, and solving it for u of t, we get this approximation. Likewise, for u of x in this situation, we have the u of x linearization that we saw for, and you'll see that these two forms look identical. As you would expect, we just interchange the variables delta x and delta t. Okay, plugging in our values for t equals 0.01, so a very small step in time, and a much smaller step in space, 0.005. We get x is at x is equal to 3 and 2. What that means is that this x here is x plus 0.0005, and t here would be 2. Likewise here, this delta t here would be 0.01, so this would be 2 plus 0.01, or 2.01. That's what we'd be plugging into that u function that we saw at the beginning, which was that x squared plus the other terms. Okay. Plugging these numbers in directly, you get that u of t, the partial evaluated at 3,2, is equal to 25.06, and u of x at 3,2 is equal to 116.27. So you'll notice that this was 25 is the exact value for this derivative at this point, and 116 was the exact value. So while they're not exact, they're super close. They're very reasonable first order approximations to the actual value of the function. Okay. All right, so plugging these in. Now we're going to look at the second derivative. The second derivative is a little bit more difficult, a little bit more challenging, and a lot of that has to do with the stability of the higher order terms. As you go out, squaring and cubing uncertainties can greatly magnify those, and so to create a more stable approximation scheme, we're going to employ a trick here. So our final result is down below in the green box, but let's see how we get there. Okay, so we're going to expand the Taylor series out to the second order and then ignore all higher order terms. That's what the HOT stands for. So this would be like your third derivatives, your fourth derivatives, and so on. And we're going to look at a step forward in time and solve for that u of x. And we see that here. But there's no, mathematically speaking, difference between stepping forward in time or position and stepping backwards in forward or time. So, in time or position, sorry. And so let's go ahead and try that and see that if we step backwards in time, we end up with a very similar looking formulation with a small difference in terms of the linearity of the step. And so finally, our next goal is to think about where we're at now, or we're going to consider an average or a weighted average of where we're going to, where we're coming from, and where we're currently at, which means we're going to set these two derivatives, these two approximations equal to each other, and solve, which yields then finally a second order approximation that is much more stable than the original approximation and just stepping one direction. Okay. Now to our physical system. we have 0, 1 over n, 2 over n, and you can see what we're doing here is we're breaking up this length of n, very much like a Riemann sum, into n equals subintervals. And what we're doing is we're creating a grid along the rod to check the temperatures at these different locations. Okay, that's what we're looking for. Okay, so dividing these up into n pieces along the rod of length L, we end up with a system that we can create a linear system from. We'll note here that the boundary conditions have at the endpoints when x is equal to 0 and when x is equal to L, we're going to hold these temperatures 0. So the temperature on the boundaries of the rod will be 0, and that's where the heat will actually be leaving through in our system, in our model. We're going to assume that the rod itself is actually insulated so that no heat is flowing into or out of, and so the only way that heat can move is through the endpoints. All right, and so that's what we're going to be measuring with our function, and you'll also notice that our domain for our space-related variable is the length of the rod, and our time is going to evolve for as long as we want it to, from whenever we started the clock until some later date. Okay. One thing that I wanted to point out that I think can be very confusing, especially when you start to solve partial differential equations in classes beyond this one, is the boundary conditions and the initial conditions sometimes can yield to weird things. So in this particular case, you'll notice that when t is equal to 0, it's telling you that no matter where you're at in position, the temperature value is equal to 1 in whatever units we're measuring in, which means that both at the end caps here, at x equals L and x equals 0, the temperature is actually 1 before you start the clock. And then by some magic, as soon as you hit the start button and the clock, the temperatures here drop to 0. But they are, for the sakes of our model, actually equal to 1 prior to, and you'll see where I points that out in the actual derivation of the numerical values for this. But I just wanted to point that out explicitly. That can be kind of confusing if you are getting new to this and also kind of not sure or uncomfortable with the notation. So it is actually true that we are assuming that it is equal to 1 prior to starting the clock, and then instantaneously jumps to 0 once we start measuring the time. Okay. So here is our example. We're going to use capital T for temperature just to differentiate the physical system that we're measuring versus the generic kind of thing. And this is the heat equation here, which you saw earlier. So the partial of T, so of our temperature measurement and time, how is it changing? Changes with the second derivative of its spatial variation. So that relationship, and here are the boundary conditions and the initial condition. Okay, so with this in mind, we're going to linearize this system and then look at how we can use linear algebra to solve it. All right, so just like in our previous system, we have the first order derivative with respect to t has that same exact form, just replacing u's with t's, capital T's. And our second order derivative has a similar form, but there's a couple of things to point out. Specifically, you'll notice that there's a lambda value here, and then a 1 minus lambda value. And this comes from a numerical scheme approximating this value. And when lambda is equal to 1/2, we have what we call the Crank-Nicolson approximation. And the reason for this is that it allows us to create a more stable approximation. And what I mean by stable is that when you look at the step size, the delta t or the delta x, a stable system is is not going to be sensitively conditioned to if your step size is 0.1 or 0.6 or 1, you'll still get a reasonable response out. A sensitive system would mean that if you went from 0.1 to 0.13, for example, you may get a very different numerical result out of your approximation, meaning that the system itself is very sensitive to the initial size of your step, okay? Which means that if it's sensitive, you're going to have to take small step sizes, which means that your calculations could go on forever and could actually run the computer doing the approximations out of memory. All right, so with a little bit of cleverness and some algebra, we can actually make a scheme that is not so sensitive. It's what we call stable to that approximation, which is what we're doing here. All right, so for us, we're going to let lambda equal 0.5, like I said, or 1/2. That's the Crank-Nicolson value. And so let's dive into that. Okay, so we're going to be modeling the rod again with no heat flow. It's insulated with these initial conditions. And we're going to assume that our rod length actually is 1. So we'll make some really nice approximations in a minute once we do some of the algebra and linearization processes. Okay, so we're going to set the two equal to each other. And these are just taking the two approximation schemes that we saw previously and setting them equal.
Daddy.
All right, so sorry about the interruption there. My son was taking off for a second. All right, getting back to work here. So once we kind of start to solve for the future terms, which are the terms with the plus delta t, these are the terms that are forward thinking or forward in the future. We don't know what those values actually are. We know about our state currently, our system currently, and so we're going to isolate those variables on the left-hand side, and all of the known quantities we'll put on the right-hand side. So all the terms that don't have the delta t in them will be the terms that are on the left-hand side. And those are what are going to generate our system of linear equations. Just a note for notational purposes, as you get more experience with equations of this form, partial differential equations in particular, you're often going to see lots of constants floating around. And so a very common trick is to rename constants, so to group them together in some form. And so we've done that with the constant r. So we're going to take r and define it as the ratio of delta t over delta x squared, just for making the purposes of both the algebra but also the calculations a little less cumbersome. Okay, so we're going to move we're going to plug in our substitution here, and then we're going to move all of the terms with the t plus delta t to one side and all of the terms that we know about over to the other side, to the right-hand side. Okay, and in doing so, what we're going to end up with is something that looks like this. So this is our stable Crank-Nicholson approximation scheme. You're going to end up with, on the left-hand side, negative r over 2 times the temperature as a step forward in both time and space. I said that backwards, but in space and time. And then with a little bit of simplification here, you get and then also the temperature of where you're at currently, but a step forward in time. And then you're going to subtract from that the temperature 1 step previous to you, 1 moment forward in time. And you're going to balance that with the equality of the temperature of where you're at currently, 1 step behind you at the time currently, and then also the temperature of your current location in time, and also a positional, the temperature at the place 1 step in front of you at your current time. Okay, we're going to choose these values for our physical system. We're going to let the length of the rod be 1. Our step in x, since our stable system is allowing us to take a larger step, we're going to take some bigger steps here, primarily because adding more delta x's to it will give us a better approximation to the physical example, but it doesn't create a better understanding mathematically of what's happening. Since this is just to kind of get your feet wet and to make you explore this process, it's just more convenient and not less cumbersome to choose a larger step size. Likewise for delta t equal to 0.08, if we plug those numbers into our definition of r, you'll see that you get a value of 2. Okay, and simplifying, so plugging those values into this equation above, you finally get the approximation scheme that we've been looking for, which is what we see here. Okay, and so we'll use this on the next part to actually calculate and generate our system. Okay, so here is our system. Up here, you'll see this is the approximation scheme. I found it helpful to have it in front of me so we can generate the coefficients. These temperatures at these locations are the ones that we're looking for, and we don't know these yet. We're looking at the temperatures as they evolve over time. And we do know the temperature at each of these positions at our current time. So we don't know what it is in the future. This is what we call implicitly defined. So the Crank-Nicholson process has some explicitly defined things, but also some implicitly defined things. So that creates then the need for the system of linear equations, which we're going to generate. So imagine this is our rod of length 1, and we've partitioned the rod into these individual nodes. So imagine that these are maybe where the sensors are at for measuring the temperature. in a real physical situation. And again, there was no heat flowing out of the rod through the sides. It's only through the ends of the rod. So U of x equals 0. You have that the temperature is equal to 0 after we start the clock. But remember, and you can see that here, that before we start the clock, the temperature at T1 and at the other end at the length of 1, those temperatures are 1 originally, initially speaking. Okay, so before we started the clock, they're at a temperature 1, and as soon as we start the clock, they magically drop to 0 temperature and then remain there for the rest of the time that we're running the clock. Okay, our positions are 0.2, so that creates 1, 2, 3, 4 interior nodes, and then we have the 2 exterior nodes. Okay, and we do know something about what the temperature at the exterior nodes. They're in both cases equal to 0, so that's going to be very helpful for creating our system here. Okay, so utilizing this side here and plugging in the information, we know each of these values, and each of those values turns out to be 1 for the temperature along the rod in our initial temperature step. Okay, and that is to say, before we started the clock, the temperature was 1 everywhere, and so what is the temperature when you look at it outside of that first step? How is it changing? And that's what we're trying to figure out. We don't know how the temperature along those parts are changing. We do know how it changes at the endpoints. It goes to 0. Okay, so let's figure this out. So if we start at our first step here, okay, the temperature to the left, we already know what that temperature is. That's 0 once we make our first step. So we're here, our temperature to the left, this is 0. This one we don't know, but we do know its coefficient is 3, which is why there's a 3 showing up here. Okay, and then if we step to the right, what is the position to the right? Well, that's this position here. We don't know what this temperature is, but we do know its coefficient is -1. Okay, so this little group of 3 here comes from our first step when x is equal to 0.2. And the coefficients correspond to the coefficient matrix. The unknowns, of course, are the temperatures. T1, T2, T3 is, or T0 is actually known. Okay, so if we step along our rod into our next internal location at 0.4, okay, we see then to the left is a temperature for T1. We don't know what that is, but we know what the coefficient is. It's -1. The temperature at our second step here at 0.4, we don't know what it is, but we know the coefficient is equal to 3. And likewise, one step to the right, we don't know what that temperature is, but we know its coefficient is equal to -1. Okay, so that's where this 3 step comes from. And then these temperatures we're not there yet, so we don't know what they are. They're 0 with us. Okay, and then we step one more to the right, we're at 0.6, so the temperature behind gets a -1 coefficient. Where we're at is at 3. And then we step one more to the right, that's at the 0.8 position, and that has a coefficient of -1. So you can see that you're going to get these strings, and then if we step one more position to the right, okay, we're here at x equals 0.8. Now, an exciting thing happens. We do know the temperature at this location. It happens to be 0. So our temperature to the right happens to be 0. Our current location, we don't know what the temperature is, but we do know a coefficient is 3. And the temperature to the left, we don't know what that temperature is, but we know that the coefficient there is -1. Okay, and now if you look at the system, I've kind of highlighted it here in this black box, you'll notice that we end up with a system of, in particular, right here, since this is before we started the clock, this system right here of these 4 equations and 4 unknowns is exactly equal to this. So if we were looking at our linear algebra sense, we would have 4 equations, 4 unknown temperatures, and the 4 temperatures are our variable x. So our a are these numerical values for this matrix, our x are the unknown temperatures, and then our b, so ax equals b, our known temperatures starting the equation would be the right-hand side that we have equal to here. All right, so let's put this in matrix form at our initial step of 0.08. And you'll see that the matrix form of the coefficient matrix looks like this. Here's our column vector of unknown temperatures and our column vector of known temperatures. So doing row reduction on this, we end up with the temperatures internally. T1 is 0.6, T2 is 0.8, T4, or T3, sorry, is 0.8, and T4 is 0.6. So now, if we want to know what the temperature is, one more delta T in time, all we need to do is take these resulting temperatures, because these are the temperatures now, after 1 delta T, and plug them in for our unknowns here. So you may be wondering, well, how come these aren't 0.6, 0.8, 0.8, and 0.6? That's because we have to use this temperature scheme to figure out what the temperatures are at that location. So just to plug this in, you have 0.6, that's our current location, right, at T1. Okay, T0, it's 0. And then you have the next one over is 0.8. So you have 0.8, and this one is 0. So you have 0.6 minus 0.6 from 0.8 gives us the 0.2, which is why in this solution, that's the temperature, the new temperature at T1. Okay, before we take that step. Does that make sense? Okay, let me do one more just to make sure we're all on the same page. So here we're at 0.4. So this is our current temperature. So you can see it here, right? Looking one back, we have a positive 0.6. We're subtracting from that our current temperature, which is 0.8. So we're at a negative 0.2, the difference between these two. And then we're going to add to it another 0.8. So negative 0.2 plus 0.8 gives us a 0.6, which is where this temperature comes from. Okay, so I hope that makes sense where each of these temperatures come. So these give us then the relationship to derive the value for the temperatures at this new time frame. Okay, and then we have the coefficient matrix. It doesn't change for each iteration, which is a nice thing. And so we're going to do the exact same thing. We're going to augment this matrix, the coefficient matrix, with the solution matrix to find the temperatures at this time. And we find the temperatures are 0.2, 0.4, 0.4, and 0.2. Okay, so if we want to step one more delta t in time and look at 0.24 seconds, we can do that. Again, finding that the temperatures, the current temperatures now are uniform across. We have a 0.4, so that's this one. Oh, sorry, if we're at T1, we would, if we're at x equals 0.02, okay, we would subtract this location, but that's 0. So it's really just our current location, which is 0.2. So it's negative 0.2, and we're going to add to it the position, the temperature of the forward position, which is 0.4. So 0.4 minus 0.2 gives us a 0.2. So that's the current, that's the temperature at x equals 0.2. Stepping one to the right at x equals 0.4, we have our temperature back there is 0.2. Our current temperature is negative, or is 0.4, so it's a negative 0.4. So that's a negative 0.2 putting these two together. Then we're adding a 0.4 to that location. So negative 0.2 plus 4 gives us a 0.2 again. And so that's how we're creating each of these column vectors. Okay. And then so reducing the temperature one more time, we're solving for the temperatures at the third step in time, we get that the temperatures are 0.2, 0.12, 0.16, 0.16, and 0.12. So we can continue this process and look at how does the temperature change at each of our locations over time. And to put that into perspective, okay, so here it is at our fourth step, utilizing the temperature gradient from before. We find that the temperatures are at 0.07, 0.12, 0.12, and 0.07. So they're cooling off significantly, but not nearly as much as they were originally. So if we wanted to see that in a picture form, we can look at how the temperature profile changes by looking at the graphs of each of those temperature profiles. So initially, before we started the clock, everything was at a uniform temperature of 1 in whatever units we're using. Okay, and then at our first delta T, we found that the temperature at the endpoints dropped immediately to 0, and the temperature distribution in the rod dropped significantly at each of the indexes, right? So we had a 0.6 and a 0.8 and a 0.8 and a 0.6, and then in our second step, we see a significantly larger drop as the temperature comes to equilibrium quicker between our second and third, our first and second. And so the temperature drops here, and you can see it's starting to become much more uniform across the profile of the rod. And then our third iteration, we find that our temperature drop is almost uniform across the thing. So you can see it's significantly less steep, meaning the temperature difference between the ends of the rod and the center of the rod are becoming closer and closer to 0. So that's how the temperature evolved in time after 4 iterations of time. So you're going to be doing a very similar thing with a slight difference in the way that the system is set up. The rod, in your experience, will not be insulated, so heat can flow in and out of that. So you'll figure out a way to deal with that in your approximation scheme. I hope that makes sense, and I hope this video was helpful. I'll see you in class.